So I work for Osisko Gold Royalties. I've only been there since September. So it's a royalty company. So we provide capital, so money to companies who are either building a mine or they need to update a certain part of their mine. And then in return, we get usually a portion of the revenue that they produce or a portion of the metals produced. Last year we grew, we almost doubled in size. We bought a gigantic portfolio. Our main assets are in Quebec and Canada, mostly gold. We have a little bit of diamonds. And we're pretty aggressively trying to expand and looking for opportunities. Like I mentioned, the Gold Rush competition. So basically, this is a junior company which had a project in Abitibi. They wanted to see if they couldn't find new ideas on exploration targeting. So they released their data and they challenged everybody to come up with some new ideas on where they should be drilling. So we took together with my team here. There's JP, who's a geologist, and Doug, who's a chemical engineer, but he works as a geometallurgist. So we put together this package. Basically, we took all of the geological data we could find, we interpolated it and extrapolated it into a block model covering all of the property, and then we applied two separate functions to try to pick out what are the best targets on the area. The first one is a more classical approach, weight of evidence. So using our understanding of what is controlling mineralization, so alteration, proximity to faults, presence of certain intrusions, and then add a score and sort of add up those scores to see where we should drill. And then parallel to that, I took the data, I gave it to Doug, and I said, do some fancy math on here and see if you can come up with something. And so the method he applied, we'll talk very briefly about it, but he's really the person who led it. But you know, after that, we won the contest, and people expected me to understand what that component was. So basically, I had to go and learn all the aspects of machine learning, and just to give you an idea of how low the bar is set right now for a machine learning expert. So for me, I think there's an opportunity. It's a very powerful tool, but there's also a danger of people trying to use it and don't understand what's important. So this is sort of the basis of this talk. There's another big Happy Gilmore check. So why is this important? We're getting less and less good or less and less efficient at finding new ore bodies. This is a classic chart by an Australian fellow called P.H.D. And essentially the discoveries, a rate of discovery is half of what it used to be in terms of dollars spent versus tons discovered. We need to sort of think outside the box and find new ways to get better at finding new deposits. Big data is another term that's thrown around, and what we have new now is several new tools, which is getting us really dense, high precision, but also a large volume of data. So CoreScan, for example, is a technology that's basically hyperspectral scanning. We're used to seeing those tools from satellites or from airplanes, but now it's really like on a very thin strip of core. You're getting basically 1 million pixels of information, mineralogical information per meter, so that's extremely dense information. We're also developing new, more powerful geophysical tools, but more importantly, inversion tools and different algorithms. So we're getting a lot more data. It's following the capability of our computers to take it in and process it. And then it's just a matter of how we're going to use it. So I've been following machine learning from a distance for a little while. I'm interested in Tesla and autopilot and autonomous driving for a little while. So basically in 2005, the American government had a problem in Afghanistan. They were losing all kinds of casualties and injuries due to people getting hit by roadside bombs. And they figured if we can get trucks to drive themselves, then we don't have to put all these people in danger. So they put out a competition called the DARPA Challenge in 2005. And several universities and different technology groups built these cars with different sensors on them to try to figure out how to get the car to understand where the road was and stay on that road. So the first year basically was not a success. Most of the vehicles saw their shadow and freaked out and turned around and hit a wall, or this guy just flipped over. But the very next year, several groups completed the course. So it's something like 100 kilometers through the desert. winding roads and cactuses and all kinds of things. And the difference between the 2 years wasn't that they had better sensors, it was primarily because they had better algorithms to understand, to crunch the data, but also they had a year to teach the robots the difference between a shadow and a cactus and all these things. And today you can buy a car which basically drives itself. You can go on YouTube and see this crash avoidance. Basically, the view is from a Tesla, and you saw a crash that was going to happen in front of it. Not the LiDAR, but the radar detected a car that had stopped suddenly, and basically the Tesla stopped ahead and saved it. So we're going to see more of this for sure. But it's just an example of how this is changing, and we're going to see it's become a buzzword, machine learning and big data, and we're going to see a lot more of this type of thing. The other thing that's changing is it's become very accessible. So Microsoft has a platform you can go on tomorrow, sign up, and get and do machine learning. You basically take your data, put it up on the cloud, click some buttons, and it shoots you something, and it gives you good confidence that it's really good because it's very fancy. So it's getting accessible. This is a little bit, they're a little bit of a crack dealer, so eventually you have to pay. The first one's for free, and then eventually you hit your limit, and they come back like, whoa, I can help you, but you're gonna have to pay. So how can we apply machine learning to exploration data? So there's lots of problems with our data. First of all, our data is quite clustered, and it's often clustered around what we know already. And what we want to find is new deposits. So we want data where we don't have already deposits. The data is very heterogeneous in terms of positive examples and negative examples. So if you're training a machine learning algorithm to recognize the difference between cats and dogs, then you want to show it about equal number of examples of cats and dogs so that it can learn the particular differences. And in mining, then you want to show it about equal number of examples of cats and dogs so that it can learn the particular differences. And in mining, obviously, we don't have lots of examples of success. In certain cases, we have no examples of success. If we're going to a new greenfields area, we can't show it what we're looking for. Also, the algorithms are very good at identifying very specific things, but often we have different styles of deposit. The host rock will change and things like that. So we need to teach the algorithm to look for different ore deposit types. And sometimes we don't even know that we have it, so it's going to miss things that a human geologist might pick up. The other problem we have with our data is that it's very uneven quality. So this is a difficult thing where we have maybe an airborne mag over the entire property, and then we come back over the area of interest, and then we do ground mag or conductivity or geochem soil, but we don't cover everything. So now we have an area with very good information, and the rest of it is not so good. So you have to figure out a way to decluster the data and treat it in a very good way. So the answer to the question is our data good for machine learning? No. So there's different ways of dealing with this generally, and we'll talk a little bit about how we can do that. So some prerequisites I think are important. Pre-screening of data, garbage in, garbage out, obviously. Also, I've had lots of discussions on whether or not the geologist should be imposing some interpretation on that. So should we be giving it a geological map? Because obviously there's a bias on that. We're placing faults in different units. So that's still up for debate, I think. I think for now we should all be trying to use methods that are gray boxes at least. So if you hear deep learning and deep neural networks and things like that, often those have several layers of contortionism of the data, and it's impossible to see which features of which data type it's actually selecting to make its prediction. So it's hard for you to validate whether or not that's okay. So sometimes, most of them, it's not purely transparent, but a gray box machine learning technique, you can actually see which of the elements it's actually using. And I'll give a good example at the end of that. We want to be able to quantify benefit, so we can actually, I'll talk about how we can do that. We want to maximize true positives. So essentially we want to find fewer holes to find the ore. So if your machine learning targeting map is drill 50% of the property, you're not actually adding any benefit because you can't drill everything. And then the flip side, you don't want to miss anything, okay? And so there's always levers and knobs and sliders that you can use in these machine learning techniques to sort of balance that, so you have just the right amount of targets and you're not missing any of the opportunities. And so to explain what machine learning does in the very simplest terms, and I'm only talking about supervised learning, so we already have examples of success. So in this case, we only have two different data sets, data types, cyanite and arsenic, and we can plot them in space. This is our examples of success and failure. So these samples or blocks or cells we know have mineralization, and these ones do not. And the machine learning algorithm is just a line which defines the contact between those two. Okay. And most of the time, if this is the actual data set, then I don't need a computer to tell me what it is. Often the correlations are not that great, it's very fuzzy, okay? And then we can take, now we're only talking about two different factors, but if we add a third factor, now you can imagine that this is no longer a formula which defines a line, but now it's a surface, and it can have bumps and grooves and different things like that. And if we go into more dimensions, we add more data than our human brain can't really comprehend. But basically in hyperspace, there's a surface which defines its prediction of what's ore and what's waste, okay? And I have a paper actually that defines this. I'm not going to go through it in detail, except to say, and this is the steps I think are the most appropriate in terms of applying machine learning to exploration. But one thing that's important is to, again here, this is our machine learning, the algorithm, the simple definition of it. But typically what's important is we isolate part of the data that the computer or the algorithm can't see, so that we can come back later and test whether or not it can make those predictions. So we keep some examples of success, known success and known failure. And then at the end, we're like, well, okay, now I'm giving you back the success. How good are you grading yourself? How good are you at defining that boundary? And if you're interested, just reach out to me. My cards are there, or LinkedIn, and I can send you a copy of that paper. And then the different algorithms have different strengths. So this is a case where we're underfitting. So my 9-year-old daughter can do a better fit on that. We can go to the extreme where we let the algorithm be very, very complex and do some nice carving, except it's trying much too hard to get the answer exactly right, and it's going to leave behind some examples of success. So this is coming back to the levers, so we can adjust how hard it's working to get all of the examples correctly, and then this is sort of the Goldilocks best response. And at the end, what we're really looking for is to have a score. So in this case, we had lots of 3D information, so we created a 3D cell. So each one of these is 50 meters by 50 meters. Obviously, you scale it to your property, and oftentimes your data is not sufficiently 3D that you might as well just do a 2D unit. And then each one of the blocks actually represents a prospectivity score. So the hotter the color, the higher the grade, and then anybody who's even not a geologist could say, well, why don't we drill this one? And you're like, why don't we? So the algorithm we use for the competition is called Bayesian Gaussian Process Latent Variable Modeling. It has a lot of good aspects. It's pretty good at filling in the blanks, so it's using some geostatistical methods, essentially multiple indicator crane to fill in the blanks where it doesn't have data. It looks at all the other data and tries to figure out how to fill in those gaps. But unfortunately, it's a method that's black box. So when I said, Doug, tell me, like, what is it using to make the prediction? You have to sort of find a roundabout way to get me that answer. And it's quite good actually at compressing data. So we think, oh, with the computers we have now, we can crunch any number. But this is the kind of situation where you press go, and then you're like, oh, I'm going to go for coffee. When I come back, it'll be done. And then you're like, no. And then you go, well, I'm going to go for pizza. And then when I come back, and then the next day you're like, oh, shoot, like I got to go back and start over and then reduce the number of data I'm allowing or reduce the cells or something. So this method actually has some compression of data, something similar to principal component analysis. So it's nice and easy to crunch data. So everything that I've talked about is with respect to supervised learning, machine learning. So we know we're feeding the algorithm examples of success, but we can also feed it raw data and say, make a decision, classify the data in different classifications. So we're lucky that we're late to the game. Lots of things have been developed for us. So this is an example in biology. So this is being used for evolutionary biology and things like that. But we can apply it directly to geology. So this is actually geological data, and it's basically trying to classify, in this case, there's sedimentary rocks. So maybe these are all calcareous, and these are all sedimentary detrital sediments. And then the closer the branches are, the more related they are. But we did things similar to this, but for alteration. So again, alteration packages that are more similar, it'll do that. And then you can plot that in 3D, see the relationships, how they plot in 3D. So what's next? We have chips in our phones that do AI now. So like the hardware is getting better, the software is getting better, and it's a buzzword. So if you're starting a new company like Bitcoin, blockchain, machine learning, just stick that in the name and you'll do a lot better. And in your new jobs in the future, somebody will eventually say, hey, you're young, you must know this stuff. Can you like try this on things? So I think it's worthwhile to, if you have the opportunity, to take a course. Lots of YouTube is my machine learning university for me. So lots of great information out there. So expect more. One thing that I haven't seen yet on this scale is actually everything that I spoke about is basically each cell is like an individual isolated unit. But in geology, things are linked. And I haven't seen yet anybody take sort of regional connectivity between links. So if this is a porphyry system, we know there's some pattern of alteration that we should be detecting. But if each cell doesn't know where it is in space with respect to its neighbors, then we can't really make any predictions based on that. But this is extremely hard computationally, because if you think each cell needs to know where its neighbors are, and it gets really, really heavy. The holy grail, though, is having an algorithm which you can learn in one area. So this is a project we had done in Mauritania. And then take what we learned there and apply it somewhere that we don't have examples. So, let's say we have the exact same rocks in Greenland. Can we take what we learned, and apply it somewhere else? And that's going to be a very difficult project. So powerful and perilous. We're going to see a trend towards more qualitative data. So like handheld XRF, I want to have handheld XRF on everything all the time. It's cheap and easy and to do, so let's have more of that. We should have multidisciplinary teams. So there's very, very few geologists that know machine learning, and there's very few machine learning people that know geology. So bring everybody towards the center, but at least you need one that knows a little bit of each. And then computer power still has its limits. So when I made this talk, I thought like, geez, what's the worst case scenario? And I thought, this is perfect. So let's say you took Abitibi in Quebec, lots of gold mines there, and you did this amazing compilation, you did mag, connectivity, geochem, all this, and you're like, oh, you know what? I can go to Google Maps and feed it satellite images. Maybe it'll see a certain plant or something that it likes. And so you stick this in as a layer, and you go in your deep, deep, deep learning, and you let it figure out what's going on. So these are different mines that we see in Abitibi. So you see a little pattern here, lots of gravel roads, you see lots of colorful lakes. Again, this is really good. So what's the computer going to predict now? What it's going to do is actually ignore all of the other great geological data you have, because it can get 100% precision based on these pictures. And basically, it's going to pick colorful lakes and gravel roads. So Tim's golf course, that's a great place to start. The municipal dump in Val d'Or, like, geez, I know where the next mine is.
Well, don't laugh. Have you drilled there yet?
No, I know. And this one actually is a really good target, because it's like not that far from the big pits that they went right in time. So, buyer beware, be careful, do your homework, and like look at what it is. At the end of the day, you get a series of targets. You need to do some homework after to make sure that they make sense, and geologically speaking, they fit into what you want to do. So any questions with respect to this? Yeah.
What do you think about using machine learning as alternative to the classical estimation for resource estimation?
Good question.
Is it better than kriging? Is it better than simulation?
I think the application would be most suited to getting your geology model right. Having sold resource estimations to no problem. Actually, it's good. There's especially in Canada, there's a reticence to apply highly statistical methods. Like even kriging was like, well, why would I use that? So to do that step, I think would I think there's going to be use, but it's going to be more to get their solid correctly, right? Like learn what a vein looks
solid
like.
is definitely the first thing, of course. I mean that if we assume that the geology is okay, what would predict the better results? Grading or say simulation or?
I don't see any big advantage, but I'm sure people will try, and I've had other people ask that same question. So,
well, you've hit on something I've always wanted. Like, I just spit in a vial and mailed it off to Ireland, and it told me my grandparents came from Belarus, which is true. So I want to do the same thing. I want to send them some earth, and here's some nickel. And by the way, there's the same thing in Mongolia.
Yeah.
So can't we get to that step?
I think we can. The issue is going to be, I think, leveling. So the exact example where I gave, where learn in Mauritania applied to Greenland.
Right.
Well, Mauritania is covered in saprolite, so the rock has rotted away, and now it's got this layer of gunky soil.
Mm-hmm.
So your mag, even if it's exactly the same rock underneath, your mag is not the same. It's attenuated by that soil.
Mm-hmm.
Everything is sort of different, and even like the Mauritania example, the soil chemistry works like bonanza. Like it's all of the deposits practically in Africa and West Africa are basically on soil samples,
mm-hmm.
and they go back and do a little bit of drilling, and then they find the structure.
Mm-hmm.
So in that case, we actually had to hide. We realized that all the algorithm was doing is telling us where the soil anomalies were, and the client was like, no, I know those, like show me something new. Mm-hmm. So we actually hid the soil anomalies, and we said, detect where the soil anomalies are. And in that case, it gave us new anomalies, which actually one became one of their new showings. So I think it's possible, but it has to be done in a very specific way. And just like if you think about all the different deposit types, like even in a given area, you have 3 different flavors. So how do you capture every flavor of deposit?
But 10 years ago, nobody thought we'd be spitting in vials either, right?
No, no. I think we'll get there, and somebody will do it, and somebody will make a lot of money doing that. But it's going to be difficult. Yeah.
I just have a question about what you're talking about unsupervised machine learning.
Sure.
So is that meaning like, because in your example here, you have this like strong correlation between say two say attributes or something like that.
Yeah.
But in some cases, maybe you don't even know what correlation there is yet. Like,
exactly.
You may not even know what you should be looking for in terms of the pattern, right? And is that what you mean? And then if that's the case, how does that work? In terms of it discovering new patterns that you haven't thought of yet?
Sure. So for me, the most obvious application is basically you feed it a bunch of geophysics, and you say, find me domains. So if you say, find me 2 domains, it'll be like sediments and volcanics. And you're like, okay, now show me 5 domains. It's like, oh, I can see sort of this volcanics is actually 2, and then that. And as you push it to lump things together, and you're not telling it that what recipe it is, you're just like categorize things. Eventually, it'll have things that don't fit in very well, right? So the fit will be low for a few things, and deposits are inherently complicated, messy things. So you might, if you ask it for 20 things, the 18th and the 25th things might be little chunks that don't fit in very well with all the other stuff, and those might be your targets. So, but yeah, so potentially that's what you're looking for. But most of what people, when they talk about machine learning, is it's supervised. So you're showing it what it's looking for, and you're showing what pattern to look for over and over again. So, but I think there's potential to. And like in Greenland, like let's say you're in a brand new area, well, you can't teach it because you have no examples. So I would start with something like that and see what patterns it pulls out and what doesn't fit in a specific category. One last one.
Sure. You've got some nice visuals up there. So I'm wondering what patterns you use for your modeling and then your visualization.
So this is an app called Prezi. It's on the cloud. It's free to use, but if you use it for free, then it's public. You can pay like, I don't know, $10 a month, and then you can download it and have a copy. For the software, we used a bunch of stuff. So it was actually, the competition was sponsored by Leapfrog, so we use Leapfrog. This was our in-house software for for resource estimation by SGS Geosite. It's called Genesis. Some of the stuff is from Google Images, but lots of statistics. Again, it was a lot of in-house stuff, but you could do most of it in Leapfrog, and then online with Azure. And if you're not scared to learn a new language, go learn Python, and then you just download the libraries and click go and just do some of that. All right. So if you have any more questions, please don't hesitate to reach out to me.